down is said to be separable if there exists a countable dense subset. Okay? So we have already seen some examples. So here is one example. So R with a usual topology. Is separable because the set Q, the set of rational numbers, is countable and dense in R. Okay, that is its closure. Therefore, it is separable. We have already seen some examples where so we have already seen a theorem that every second countable space is separable. Yeah, separable. So question is separable. Okay, the separable space like second countable spaces. So please think about this. Okay? Think about this. We have seen several examples where where a space is not second count. So can you tell me some of the spaces which are not second countable, however they are separable. Okay, so here is another example of separable space, and it will give you a hint for our question. The space RL, which is R with the lower limit of R. So the Schrodinger line. Okay. So R with lower limit topology is separable. So same reasoning, because Q bar is okay. So what can you say about RL? Is RL second countable? So we have seen this thing. So here a hint for it is RL second countable. Okay. So you will get an answer on this question. Next example. So what about R with the co-countable? Topology. So let us see. So assume that R, say let us denote co-countable topology by tau CC. R with co-countable topology is separable. So what does this mean? This means This means there exists a countable dense subset. Okay? Say A. So this means A is countable and A bar equal to 1. Okay? So, but what can you say about all countable sets in a co-countable? You know that every countable set in a co-countable topology will in fact closed. Okay, why so? So because if A is if A is countable, okay, this means what can you say about x minus A? Okay? So x minus A x minus A is A countable. Okay, is countable then. So countable implies x minus A is open. Okay, which implies A is closed. Thus, what do we know about closed set? About closed set, so for each closed set, A bar equal to A, okay? Which is clearly not to R in this case. So this assumption is wrong. Okay? This assumption is so this kind. So this means supplies R with the co-countable not separable. Correct? So here is some exercise, a few exercises for you. Right? So that this X is uh, okay. So this is the exercise. So how will you proceed? Okay, it is saying that discrete space is separable if and only if x is countable. So in so this is him. Okay? In the discrete space, every set, so in a discrete space X, every set or we can say set in the subset of X is open as well as closed, means closed. So this is a hint for this exercise. Here is another exercise so that X tau CF, where this tau CF is called finite topology, where is simple. Yeah? So, what can you say about so for example, take R with topology. Okay? So R with cofinite topology. So so here the main thing is what are closed sets? Closed sets that cofinite are the finite sets. Okay? The finite sets. Or the finite sets or empty or the whole of. Okay? So this means if you take so okay, I'll leave this place. So think about any countable set. Take any countable set. Okay. Take any set A, correct, and C is what would be A bar. Okay. Next thing is follow. It says that separability is a topology. Separability is a topology. So here, so is continuous edge of separable space. Okay. So how do we prove it? Proof is very easy. Let's see a proof. So suppose we have two topological spaces X and Y. I mean two topological spaces, okay? And F from X to Y be an onto function. Okay? Onto map or on function, onto map subject. It continues. So function which is continuous. Okay? So what can you say about continuous function? So for any set A, so f of A bar is contained in. So for a continuous function, we know this. Okay. So let there be any countable, countable, countable. Countable. So set of x, which is dense. Why are we taking this? Because we know x is separable. Okay, x is separable. So we are here using x is separable. So there exists a countable density. So this means a bar equal to x. So let us see from here. So what is f of a bar? F of a bar is nothing. And you know f of x is y because f is continuous. Hmm? And from here, what we have, this is continuous f. And this clearly. Okay. So this is like sandwich. This implies y equal to f. Okay. So this means f is continuous. So f is dense. Okay. Because it is countable, it implies f is countable, which implies y is separable and weird. So here is an exercise for you. So we have earlier seen this, but please try to write a proof for this. Okay? Let A be a subset of topological space X. Okay? Then so that follow. So what is this following thing? Following thing is first is density X. Second is what is a closed subset of A in X, then F equal to X. Okay. Third, non-empty basic open set. The basic open set is basic. Okay. Basic open set. It will intersect. Okay. In the basic open set will intersect. Fourth, for each X in X of the open neighborhood, X set A. Okay. Lastly, the interior of X minus A is empty. Empty. Please write a proof for this. Okay? Exercise or a homework problem, whatever. Now, let us come to another. So I should have done this earlier, but it was not in your syllabus. But I think I should teach you this part. Okay. So because it is very important. So this is called the product. Okay. So why I am doing this? So what we will do, we will see whether a product of separable spaces is again separable space. Okay. So so since we have this question, so for that first we define what a product space is. Okay. So this product. So we have two. So we will start with two topological spaces. Okay. Start with two topological spaces, X and Y. X, Y are topological spaces. And you know, X and Y both are sets. So we can talk about their Cartesian. Okay? And we want to give a topology on this set, the Cartesian product of X and Y. So define topology Cartesian X cross Y. Okay? And we call this topology the product. Called the product. So first let us see how do we define. Okay, then okay, then we will see something. So first let us define this. So system. Okay. So we have two topological spaces X and Y. We know open sets in X, we know open sets in Y. Okay. So using these open sets in X and in Y, okay, we will define a base for this topology. Okay, so for the desired topology, which we called the product topology. So let us do this. That X and Y be two topological spaces. Okay. So the product topology on X cross Y, the topology having as basis collection of, let's call this collection D of all sets of the form U cross U, where U is an open subset of X and V is an open subset of Y. I think this is clear. So let me write this D here. D collection of all product U cross V, where U is tau X. Okay, and let me call. Okay, let me call U is open. So this means U is a member of topology. open in X and V is open in. Correct? So we said that this topology is the topology having this B as a base. So let us see whether this is indeed a base or not. Okay? Let us check whether this is a base, this collection. So for that, what we do, we show two things. For one, so that for each x comma y in x cross y, there exists a base. Okay? Base member B such that x comma y belongs. Okay, this is one thing. And second thing is the following. So second thing is the intersection. Okay, y belongs to the intersection of two base elements, B1 intersection 2. Then here exists a base member B3, okay, such that B3 contains this point. This point x comma y, and it is contained with these two will be. So number one is obvious. It is clearly obvious. So one is why so? Why is it real? Because for each x comma y in x cross y, what we have is x in x and y in y. Okay. So x is the topological space, y is the topological space. Okay. So for this small x, there exists an open set. Okay. Okay. Containing x, and for this there exists V open in y such that V contains y. So you can in particular take U equal to x, and you can in particular take V equal to. Okay, this is good. So because x is an open set in x, y is an open set in y, in particular you can take U equal to x, V equal to y. So first one is well, from here what you have is x, y belongs to V. Second thing, now consider two basic opens. So B1, say since B1 belongs to B, this means take B1 comma B2 belongs to B. B1 could be some U1 cross V1, where U1 is open in X, V1 is open in Y. If B2 in B, then what you have is B2 equal to U2 cross. Okay? And what you do, you take their intersection, V1 intersection. You see, this is only set theory, U1 cross V1 intersection U2 cross. Okay? So, but this is same as U1 intersection U2 cross V1 intersection V2. Okay? So, you know, this part is open because U1 and U2 are open, and intersection of finite number of open sets is open. So similarly, this is open. Therefore, this product of two open sets. Okay? Hence, it is a member of. Okay? So, since U1 intersection U2 is X, and V1 intersection V2 open in Y. Okay? If you apply V1 intersection V2 is open in is a so is a base element. The base. So this belongs to funny. Okay. So hence this is the this funny B is a base. Okay. So let us see a schematic diagram of this figure. Suppose we have this is our y, this is x, this is y. So suppose we have two, so this one is u1, and here is say u2. So this is u. Let me make this by another color. Uh, Suppose this is so suppose this is one, okay, and execute. Correct? Then what is u1 intersection? So u1 cross v1. So u1 is which is v1 cross v1, okay, and this is cross v2, okay, and this part is so this is what v1 intersection v2. Okay. So here this B is only a base. Okay? This B is only a base, not the topology. See why? Because see this figure. Okay, here is a remark. Note that the collection B is not a topology. Okay? On X cross Y. It is only a base. It is only a base or basis, whatever it is. So because the union of these two rectangles, figure. So the union of these two diagrams of rectangles in this figure picture, okay, is not a product of two sets. So it cannot belong to B. However, it belongs to the product of. However, it open. Okay. So we talked about base, one base. So so you have seen in the in your previous lecture that there is so there are many bases. Okay, there are many bases. So can we have a base which is strictly less than this, strictly smaller this correction? Okay, so the answer is yes. We have such a base. Let us show that the following collection, which I am going to write, is a base. If B is, so let me not write B. So let me write C. If say A, the base for the topology of X, and C is the base for the topology Y. Then the following collection, then the collection say D, which is A cross C, where A comes from this funny A and C comes from this funny C. This is the base for the topology on X cross Y. Okay. Okay. So let us see. What we will show. So the same thing that we proved earlier is here. Okay. So we will prove two things. Okay, I will not do that. So let me do the following. So what we do, so to prove this, we will show that for any open set, okay, in X cross Y and any point X, Y in W. Okay. So there exists a base cross C, A cross C, where in T, okay, such that X comma Y belongs to the crossing container. Okay. So we already know what an open set looks like. Okay. So open set in W is union of union of members coming from B, means of the form U cross V. Okay? So this means every open set W contains a member coming from that funny V we saw above. Okay, this means this is of the form U cross V, where U is open in X and V is open in Y. Okay, so one open set W of X cross Y and a point X comma Y in W. Okay, by the definition of the product of the register base element U cross V such that X comma Y belongs to U cross V and contained in W. Okay, good. Because A and C are base. So these are bases of X and Y respectively. And U and V are open in Y respectively. Okay. And here you from this place, what you know is X belongs to U and Y belongs to V. Okay. This means you can choose when A coming from A and C coming from C, such that comma Y. Okay, first let me write this such that it belongs to A and it is contained in U. Y belongs to C contained in B, but this is same as saying Y belongs to C and this funny D basis for the topology cross Y. Okay, it was so we have seen what would be the base for the product topology. Let us now come to the subbase. Okay, so to define subbase for the product topology, for the product topology. So what we would first need, what we need is a projection map. Okay. So what a projection map is? Let us see that phi 1 is a map from X cross Y to X. This is a subjective. Okay. We define by the phi 1 X comma Y is the same as X. Okay. For all X comma Y in X cross Y. Secondly, define phi 2 from X cross Y to Y, which is again defined by phi 2 X comma Y is Y for all X comma Y. Okay. So these are called, so pi 1 is called the projection map onto the first coordinate, pi 2 is called the projection onto the second coordinate. Okay. Map, okay, the maps pi 1 and pi 2 called the projection of x cross y onto its first and second phase. Okay. So let us see via a figure. Okay. So here we have x, we have y. So this thing is x cross. Okay, this is x cross. So, so you know how do we define that? How do we depict a Cartesian product? Okay. Suppose this is x and this is y, and what can you say about inverse image of an open set in X? Suppose this is U, which is open in X. Open in X. Okay. So let me first define this map. Okay. So suppose we have a point X comma Y here. Okay. Pi 1 will map this point to X. So it will map this point to, so this is X and this is Y. And you, these two are. Okay. So this will be mapped to this point X, okay, and this is under pi 1, and under pi 2, this point is mapped to this point, and okay. So what happens if U is open? If U is open in X, then the set by inverse U. So let us see by a figure. Okay, let's see. Okay, suppose this is the. So what is pi 1 inverse U? So every point which is in this strip, okay, will be pi inverse. Okay? Every point which is in this strip is pi inverse U. Good. So again we have V, okay, V here. What is pi 2 inverse V? Okay, so this is nothing but this is every point in this strip. Okay, every point in this strip is pi 2 inverse V. Okay. So, so what is this strip? What is this yellow strip? This yellow strip is U cross Y. And what is this green strip? Green strip is X cross V. Okay. So pi 1 inverse, nothing but U cross Y. And which is open in X cross Y. Why so? Because U is open in X, Y is open in Y. Okay. Similarly, for P open Y, phi 2 inverse V is nothing but cross 2, which is again open. Open cross 2. Okay. And what is the intersection of these two? So the intersection of these two is the following. The intersection of these two is the following. Okay. Okay. And what is this set? This set is U cross V, which is nothing but U cross. The intersection of phi 1 plus 2 and phi 2 plus 3 plus. Okay. And you know this U cross V was a base member. So the intersection of pi 2 inverse, so we are taking a finite intersection. So pi equals pi 1 inverse and pi 2 inverse. So taking intersection of pi 1 inverse U and pi 2 inverse V, we are getting a base element. We are getting a base element. Okay. Good. So thus we have the following. Collection S U X union pi 2 inverse V B open in Y. Okay. This is the subbase for the product of on X cross Y. So let me write a proof for proof of system. Okay. So let tau denote the product topology. Okay, on X cross. Okay. And let tau dash be the topology generated by S. So our claim is to show that tau is same as tau. For this, what we will do, we will show that tau is contained in tau dash and tau dash is contained in tau. This means tau equal to tau dash. We will show this. Okay. So let us see. Since every element of S belongs to tau. Okay. Every element of see, this is nothing but U cross X. And you clearly see this is U is open X, sorry, U cross Y. And you clearly see this is in product topology, means this is in tau. Okay. Similarly for belongs tau. So do the arbitrary unions of finite. Okay, so arbitrary union of finite intersections. So okay, so this finite intersection form. So this form a subbase. So we are saying that S is the subbase. This means their finite intersection would be a base. And how do we show that this is a base? To take unions of those finite intersections. Okay. So arbitrary union of finite intersection of panes of S, they belong to tau. Okay, so this correct. This implies tau dash is complete. So one part. So another part, take any arbitrary open set, okay, on tau, and so that this is in tau. But you know, to prove that any open set in tau, so any open set in the product topology is contained in tau dash means you show that the basic open sets, okay, the basic open sets are tau dash. So basic open set are given by U cross V. Okay. So on the other hand, element U cross V topology tau is a finite of elements. Okay, we have seen this figure. So this U cross V is intersection of pi 1 inverse U and pi 2 inverse. Okay. So this means any set is a finite intersection in flux. Okay. So right, because U cross V is same as pi. So pi 1. Okay. Therefore, U cross V belongs to tau dash implies tau contained in tau dash. And we have earlier seen tau dash is contained in tau, same as tau. And we are okay. So in the next lecture, what we will do, we will generalize this product topology to arbitrary so product of arbitrary number of topology. So there might be a finite number of topological space or some uncountable or countable. So we will see a generalization of the product topology in more general conditions. Okay, I'll stop here.